get started with the last talk of the day, which is by Haghtalab from Berkeley.
Thanks for the introduction and thanks for being here. I know it's the end of the day and not very early in the week, so I appreciate that you're still here. I'm going to talk about multi-distribution learning problems, and sort of these problems are related to a range of applications, from sort of collaboration, learning fairness, to federation, and many other applications. But sort of where all of these applications start, and the motivation for all of this work starts, is that more and more in modern machine learning, we are working in learning paradigms where the data that we are working with is already spread across a bunch of different sources. Either it's naturally spread by the way that it was stored in the first place, or it's generated by just completely heterogeneously different groups of people or distributional processes. And what I really want to do is to actually align all these learning problems together, because in practice, the methods that work best for learning require really this data, and they have to sort of bring this data together. So what are some challenges that this kind of having more data and more spread out data is really giving us? Some of these challenges include the fact that the ownership of the data is now a lot more spread out. So the data is spread across multiple sources. And with the data being spread across sources or being owned by different agents, there's also different learning guarantees that different agents might want from their data. So that might mean that the solutions that we're trying to deploy in practice have to hold on multiple different types of communities or multiple different types of devices, or they have to be sort of robust to whatever happens to the current distributions that we're going to be working with. And lastly, I also have to procure resources for learning, whether it's sample complexity, whether it's computation, from the people who have the data, or from the populations who have the data, from the people who are interested in learning. And now this procurement of the data takes a more challenging perspective, because I have to align the incentives of somebody for achieving a good learning guarantees with their incentive to not want to have a lot of costs producing those resources that I need to rely on. So more data, more stakeholders, really more challenges. And these challenges that we have to deal with, that I want you to remember across the talk today, is the ownership being spread out, requiring sort of individualized and heterogeneous type learning objectives, and then thinking about how to procure resources from these multiple agents and sources. Now, why do we care? I gave you some examples of why this is happening in modern machine learning, but I think it's important to look back in the past few years, especially thinking about where these types of applications, both from really practice and also theoretical foundation, have been playing a big role. So thinking about learning from multiple distributions, essentially what we are trying to enable is we are trying to enable learning processes that would benefit multiple agents and from collectively fewer resources. And sort of from practical applications, these data sharing and joint learning, some of you might have heard of them as federated learning, collaborative learning algorithms, are starting to be deployed across multiple devices and across multiple also agencies, multiple hospitals, medical research institutes, and they're starting to play a very big role in how we learn across multiple data sources. So we really need to understand them. Besides that, they've been really behind some major scientific discoveries that couldn't have happened without sharing data across multiple agencies. This has been especially the case for medical research, and especially for genomic studies, where the data is just so spread out that without really aligning the incentives of these agencies and bringing the data across from each other and learning something that works for everyone, we wouldn't have been able to actually make these scientific discoveries. So that's kind of like, practically speaking, why these matter. But since we are at Simon's Institute and you're a theoretician, most of you are theoreticians, including myself, they have also played a big role in the foundational theory of several fields, in particular for multi-agent collaboration, welfare, perspectives on fairness, and also robustness of learning. So that's what we're going to be talking about. So really, the practical aspect of this is that these algorithms are already starting to be deployed. And what we want is to be able to get this large scale impact of them by making sure that we can actually have mass participations of these agents that are willing to give us their data, and we're able to satisfy their requirements. And we need to essentially be able to recruit and retain these learning agents and distributions. So what are some of the fundamental questions that we should be asking in this? And how is this tutorial going to prepare us in asking and then hopefully answering these questions? The first one is a very standard thing that you need to answer, which is that, fine, I have a learning algorithm. How do I know it's a good algorithm? What is the measure of success of a learning algorithm? I can no longer talk about loss for one distribution. I might have many, many different distributions. What is the right way to think about this loss when I have many different tasks? And maybe you want to think about, if I were to create some objective functions, what would be the objective function that I should create so that it will be meaningful when I'm dealing with multiple agents? The second question is, fine, now I have an objective function that maybe we all agreed on. It's a good objective function for capturing learning, like a good measure of success for learning across multiple distributions. Then what do I have to do? Well, I have to figure out, since this is a learning problem, how many resources I need to use or it's sufficient for me to be able to actually meet those learning guarantees as defined in Q1. And here, resources could be sample complexity, which is most of the focus of today's talk, but you could also think about computational resources and other types of resources, maybe communication. And here, what we really want to do is to try to rely on theory that's been developed for typical learning problems, for single distribution learning problems, and really bring it to an area that can now address multiple agents and multiple distributions. And lastly, now that we know how many resources we need, how do we go about procuring these resources? Typically in learning theory, this is just like talking about, I just need so many samples and I take it from a distribution. But now I have to figure out who is willing to give me those samples because of how much you're receiving in return from the algorithm, the learning algorithm, as taking so many other people in mind. So these are the three questions. And I want to just give you a sense of what to expect from this tutorial, because all three are important, but we don't have time to address all three in enough depth. So to start, for the first question, I'm actually not going to go in a lot of depth. And what I'm going to do is to give you one unifying model, one objective function. I'll give you some justification for this, but without going into too much detail. And I'll give you some pointers for reading more about what other objective functions have been studied and are reasonable in this setting. Part of the reason I don't want to go into too much detail here is that, in fact, I think the last talk also gave you a perspective on the same question. So let's not redo all of that. I think that was a really valuable perspective already. For the second question, that's where I actually do want to focus quite a bit, because what I want to do is to give you a unifying perspective on this multi-distribution learning problems. I keep saying multi-distribution learning problems. You probably have no idea yet what they are, of course, but I'm going to tell you how they've captured recent progress in machine learning from different communities. And my goal from this tutorial is that I give you a unifying view so that when you see these problems again, and it seems like in the past 5 to 10 years, we keep seeing them, you can identify these problems. And then you can think about how to use technical tools that I'm introducing today for the purpose of actually dealing with that kind of problem. So that's for the second part of the tutorial. For the last part of the tutorial, I'm not going to go into too much depth. There, instead of giving you a lot of technical tools, I actually want to have a call to action here. This is an area that is not developed as much, definitely not as much as Q1 and Q2. But I'm going to try to quantify some of the trade-offs that's necessary to address question 3, highlight some of the technical challenges, and then I hope to see some of you in this semester thinking about some of these problems and chatting with you guys. Okay, so that's what to expect from the tutorial. I'll go actually in order, Q1, Q2, Q3, with the amount of focus that I already explained. Before I continue, are there any general questions? Okay. So the first question was, how should we measure the learning performance across different tasks? So the typical thing that we are used to doing in machine learning is to think about average guarantees for performance. What that means is that I don't really care where my data is. I just put it all together. And what I want to do is to say that on average, over all my data sources, I have 5% error, something like that. And this is a very reasonable way to think about the learning problem when I'm thinking about average performance, especially if I think about my data as being somewhat arbitrarily partitioned across different sources. Like if it was a data center that somewhat arbitrarily decided how to divide the data to k different servers, that would be a pretty reasonable thing to think about. It's also generally good when the data is very homogeneous across sources for other reasons. Now, when is this not good? Well, obviously, we can come up with really bad examples of this, but it's usually when the data has some human and organizational aspect to it, where the tasks or the distributions or the groups or the populations are no longer homogeneous. So if I don't have homogeneous groups, it's really easy to think about, yes, I have 5% error on average, but who is really bearing that error? It's possible that one of those groups is bearing 50% of the error. And that group is like not that insignificant, maybe 10% of the population. And this is, again, I feel like last talk also talked about some of the challenges here of thinking about going beyond average performance. So what is the issue here? The issue here is that, actually, I wanted to first show this. I know I gave you something that's, of course, mathematically, it's very easy to come up with why this thing can happen. But should we worry about this happening in practice as well or not? And I just want to give you one graph here that shows that you should absolutely worry about this in practice. The fact that even in typical data learning problems, what we can see is that the average performance and sort of the worst case performance are really far from each other. And they require different amounts of work from each other. So like if I'm thinking about trying to get average accuracy of 70% in a very typical data set, what I would require is that for every sort of agent to give me a lot of an amount of data that's something like about, let's say, 40 rounds, or try to optimize 40 rounds of iterations. But then if I really want the worst case accuracy to be 70%, I need essentially everybody to do twice as much work. So what this is saying is that even in very typical, data science tasks, things that are being done on day-to-day basis, where I didn't try to craft a population that looked very different, it just was natural differences that I saw. We are seeing a lot of differences in min accuracy versus average accuracy. So this is absolutely something we should be worrying about. Now, what are some of the challenges of dealing with problems of this kind? Is that beforehand, I don't really know which distributions are harder to learn from. But if I keep talking about learning from a distribution as a task, these can have very different types of difficulties. I don't know what populations are easier, what populations are harder. In fact, the ease or difficulty is very contextual. Like whether or not a population is easier completely depends on who are the other populations. Because if there's a lot of similarity across multiple populations, well, that is naturally easier. So it's kind of a bad idea to approach these problems thinking that I need to have a prefixed budget for how much resources or how much samples or how much computation I expect from every distribution. Really, I need to actually allow the tasks to speak to me about their own difficulty and then figure out how I need to actually procure resources, how much sample complexity or how much computational complexity I need. So these are some of the challenges in this space. Okay, so what is multi-distribution learning problems? Here, I'm advocating for per group type guarantees. Again, somewhat similar to what you saw in the last talk. Let's formalize this by thinking about K populations. Populations are distributions in our lingo today. So I have distributions D1 to DK. You could think about them as patients in a hospital. You could think about them as data on different servers. What I want to learn is I want to learn a function F that is good for every population. Now, what does this mean? It means that I have some known loss function I've agreed upon. Maybe this is classification loss, whatever loss it is, somebody told me what this loss is. I evaluate every function or on every distribution. And what I want is that the worst case loss, which is the maximum over these distributions, is small. And small is shown here by an epsilon. So such a kind of guarantee would essentially say that I'm trying to uncover a universally good model, and universally is defined by being good on every population. Sometimes this is just too much to hope for, especially if epsilon has to be 0, because maybe there is no such a model that can do well. Maybe my first distribution and my second distribution are exactly opposite of each other. So this is too much to ask for. The right way to ask this question in the more general setting is to say that I want to do as best as possible. So I'm still evaluating or measuring the success of my learning algorithm as its loss on the worst case distribution. But then I compare it to a benchmark that from now on we are going to be calling opt, which is the min-max type benchmark. It's the best model, but then I took the worst case distribution in my mind. And then I'm trying to match that plus an epsilon. So this is kind of like this opt is the best I could hope for if I were to actually learn a model from the class. And this is more general. It doesn't necessarily mean that you uncover something that was universally good, but it does have this type of flavor that you did as best as you could have done if you were really concerned about the worst case behavior. Any questions about the model?
Do you want to assume that populations are overlapping or non-intersecting, or it doesn't matter?
The great thing about this model is that you do not need to make any additional assumptions. In fact, that's kind of why I introduced a general model. If we were really sticking with this, we needed to make some assumption about if they're overlapping or not, or if they overlap, they don't disagree or not. So the good thing about this model is that you don't need to make any additional assumptions. Yeah.
As specified, I could make every group as bad as the worst group.
Absolutely.
Like, would you want to sort of do it?
That's a good question. So what Sid is saying is that a pessimistic view of this is that doesn't have any Pareto optimality involved in it. You know, I could make everybody very miserable, as miserable as the worst group had to be. And that's absolutely true. This objective does not capture that. This goes to the question of how to design these objectives. There are different objectives that do take that into account. And there are also works that have looked at the Pareto optimality of these things. I'll have some citations, but I don't have a lot. I'll put them on Slack. Let me just say that if I were to kind of like change this objective so that Sid would be happier, I would change this max, right? So one way to think about this is that it's an L infinity type, norm. L1 would have been the average, and you could just put some other norm there. And those are the very well-studied, in fact, kind of these cardinal welfare utility type questions. But there are even objectives that don't fall in that category, and they're also interesting. But for today, we're going to stick to this min-max because it's very robust. And I want to also highlight the technical tools that really show themselves, like show their power in this setting best. Yes.
For some of the motivating applications that you mentioned, I would imagine that you can have an F which is for each group, like an FI. Maybe for others, this is the right formulation. Can you just speak a little bit about that?
Yeah, so that's also a good question. In fact, that will come back again in the talk. The fact that I intentionally put the same F here, the same F here. So it's true. There are applications where you can put FI on the left-hand side. And it turns out to be not, at least if you don't care about the third part of the talk, which is about incentives, it doesn't really matter. Like everything I tell you, as long as you're really trying to do this on the right-hand side, you're not making it much easier or much harder for yourself to allow people to get different functions or not. So that's about the strength of the tools that I'm going to be talking about. I want to say that while for some applications that is definitely true, almost for every application I mentioned today, you don't want to give a different FI. And I will come back I think in next slide about some of these applications, and there I'll motivate it again why it's actually important to have the same F. Other questions? Okay, so this is the setting. We're going to come back to it. I haven't really told you what this loss is. It's very general. In fact, in this generality, it includes many things in it. But just not to lose sight of the questions, especially the ones that are inspiring our technical discussion today, what we are really trying to do is to go from learning one distribution to learning multiple distributions. So this would have been the single distribution learning problem, like a single D, unknown, and I would have needed to make this type of a guarantee. And the multi-distribution just has that max of I in front of the loss. And what we really want is to really understand this, but there has been a decade of work on the left-hand side. So what I want to do is to show that not necessarily in a reduction way, but the insights, the algorithms, the techniques that we've developed here very naturally can extend to here. So instead of solving the right-hand side from scratch, I actually want to use that. Okay, now, why is this a unifying perspective? Well, actually, before I tell you why this is very unifying, let me tell you what losses we're going to be working with. The losses for this talk are losses that decompose nicely over the distribution. What does it mean? It means that they're actually relate to an expectation of some point-wise loss. What's a good example of this? You can think about this as binary classification, where there is a loss that says I evaluate f on an x, and then if it has an error, then I take the average error. Okay. In general, you just want that loss, the point-wise loss, to be like finite in range. It doesn't really matter. But in fact, to emphasize this, I'm going to use this formulation where D is a subscript. The reason I wanted to say this way is that there are losses that, in fact, the same picture that I'm talking about is still something we want to do, but they don't fall in this expectation. And one of them was the calibration loss, essentially, that we were talking about in the previous talk. It is not something that you can just write as an expectation because it takes into account the prediction of your own classifier, but it's something you could have written it this way. And it has some other nice properties. It just doesn't fall exactly under what you're going to be discussing. Okay, so for the rest of the talk, just have in mind a loss that has this type of expectation. In general, it could have been just convex loss or many other ones. Now, in this formulation, I promise to tell you that why this is, as a unifying perspective, it's important to really try to understand it so that we can recognize this type of problems. It's because in the span of maybe 2 to 3 years, at least 3 separate communities came up with the same problem as one of the important problems of their field and tried to address this problem. And these communities have actually grown almost separately from each other. So from the more theory-oriented community, this was something that we actually called collaborative learning in 2017. Part of the reason we called it collaborative learning is that the I for us was representing like a distribution that was owned by an agent. And then we wanted to really think about agents' willingness to collaborate and to help each other to learn. This is a setting that you sometimes can give different FIs, but sometimes you actually want to give the same F. It kind of depends on what you mean by collaboration. Now, there's a separate community. This was more from the federated and then later on systems community that named this agnostic fair federated learning. I introduced the fair because most people think about it as fair federated learning. And in this case, kind of the DIs represent client distributions that we were thinking about. And their main purpose was to provide these fairness goals and implications. The one that says no population is too worse off. And then from a third community, which is now mostly neural networks and natural language processing, but it actually had some of its root in theory as well. It's known as group distribution and robust optimization. And this setting focuses on optimization and not learning. What that means is that it's not really about sample complexity. It's more about, designing algorithms that can do this. they don't care about generalization quite as much. It's more of a sort of an optimization and algorithm design setting. Again, they're inspired by fairness, but also robustness. So sometimes for them, DIs don't represent actual populations, but they represent hypothetical situations where my distribution could have shifted. And I want to sort of be able to perform well in any of these weird shifts that could have happened. Okay, so these are at least 3 different communities. I'm saying at least 3 and at least 3 lines of work because essentially this problem has popped up over at least independently over at least something like 5 to 10 papers, and each within its own sort of technical tools and within its own community. So I think it's kind of important to like figure out the similarities. So we don't necessarily put a lot of effort in reinventing the wheels, but to actually have a unifying perspective on these. So as promised, for fairness and for robustness, it's actually quite important to give the same F. For robustness, that's the definition. You want the same model to do well. For fairness, there are also some legal reasons for why usually you want to have the same F. From technical perspective, it doesn't really matter. Beyond this talk, I already said a little bit to Sid, for example, which is that how would you go about, like other important questions here. So in general, like these have been studied and similar models have been studied in terms of both economic and welfare perspective on min-max objectives. So there is an axiomatic and non-axiomatic approaches to just general cardinal welfare, and then some perspective of learning. I put some papers on Slack I forgot to include here. There's also from accuracy fairness trade-offs, for example, these Pareto optimal curves. That's actually a work by Annie Liang, who is and collaborators who is this semester's participant as well. So like I encourage you to talk with her as well. So there is definitely more work that kind of justifies why you want to think about these problems, but that's not going to be the focus of my talk today. Okay, so this was as much as I wanted to talk about question 1, which was how do I set up essentially the model? And if there are any questions about the setup or the justification, this is a good time to ask, because the next thing we're gonna do is to take this objective at its face value and try to learn it. So are there any questions?
So, are we assuming that we know what group each data point belongs to, or is there a way to sort of drop that as well?
Okay. Let me go back to just say what kind of access we are going to have. Maybe I should just go here. So whenever essentially in this talk, I talk about unknown distributions D1 to dk, I give you a sample oracle access to it. What that means is that you cannot go to one person and identify which group they're in, because they could have been part of many groups. You cannot, in fact, you do not even have that kind of an access to data. The type of access you do have to data is you identify which distribution and how many samples you want to take from it. So it's very similar to kind of traditional like theory of machine learning, pack learning style. For those of you who are not familiar with it, do not worry. I will come back to that and give you a little bit just so that you don't feel like you don't know what I'm talking about. Okay, there's one other question.
So you were saying with the FIs, technically it's going to be the same methodology and stuff. So I just wanted to confirm the formulation. So on the left-hand side, you'll have FI. On the right-hand side, is it going to be 1 H star, or it's going to be like?
No, yeah, it has to be the same H star. Yeah, you still kind of evaluating yourself at that. For different reasons, if you just put different H stars, then they're really independent problems. Then you should, then there's nothing that binds them together.
If you put 1 H star, what is the motivation?
That's a good question. So especially the motivation, I like it a lot here, which is about realizability. So a lot of times what we have is that we have the same concept, but different sort of marginal distributions. Okay, what does that mean? It means that a cat is a cat. Doesn't matter, which country they live in. But the pictures of cats posted from, I don't know, the US and Iran probably are very different, right? So that's what that means, is that there would have been an FH star that would have explained what a cat looks like, but maybe the classifier that would have worked really well on the American pictures wouldn't have worked as well on the Iranian pictures. So that would be one example of this. But similarly here, like they come back again with sort of the same type of motivations. Yes. Good. Okay. It does strictly make the problem easier. I guess what I meant is that from the resources, asymptotic resources that we need to solve this problem, it doesn't make it easier. And that is partly because of the way that we have pretty powerful methods. Let me, when I get to that point out why it's okay. They're essentially asymptotically speaking, there's not that much difference between working with the same function, like giving the same function versus giving different functions. Maybe, okay, let me maybe say a few words here for those of you who already are familiar with learning theory. If I wanted to give different functions, sometimes if I had learned those functions in a good way, I could actually use their majority vote or some other combinations of them so that that combination would work across everything. So it's similar ideas that says that you sort of can always do this or more or less do this so that learning the same function, but not necessarily coming from the class, is as good as having learned, it's not much more difficult as having learned individual functions. That's all I want to say right now because it is a more advanced question and a more advanced answer, but I'll come back to that again if there, I'm sure there are still like questions about this, but let me come back to that. Other questions? Okay, cool. So let's go to the second question that we want to ask. And so we took this objective value, this per group type guarantees, we want them. Now the question is, how can we get them? How can we get them from few resources? In other words, we are really going to build a theory of either computational complexity or sample complexity. For this talk, essentially, I'm going to be talking about sample complexity only. Interesting questions are there for computation as well. So really, the type of resource I'm thinking about is information. Information comes in the form of samples. So again, I fix it. I say there's this unknown distribution. I take a few samples from it. I don't want to take too many. And we're going to focus on the number of samples. And most of what I say has some implication about computation, but I won't go into that. So again, this is the problem I want to solve. Now note that the loss is the special kind of loss, the expected loss. So this has a meaning which is about the true loss of a classifier on a distribution. Let's even think about it as binary classification. And I want to really talk about how many resources I need about this problem. For the sake of comparison, I actually want to be able to compare to single distribution. And I want to understand, like, is this easier or harder than, solving K of these single distribution problems? Is this significantly easier or significantly harder? That type of comparison kind of tells me whether this formulation is actually a nice formulation for also bringing together, especially for collaborative applications that we are thinking about, if it gives me something more than sort of ignoring everything and solving the problems separately. So here I want to go back to basics for learning a single distribution. Because we come from very different backgrounds, what I want to do is to spend a slide talking about, if you've never seen sort of the standard hack offline learnability, how would you think about that problem and why it's not that hard? And sort of we don't keep coming back to this, but I think it's still a nice exercise to have in mind just so that we have our expectation of sample complexity right. So if you've taken a course in learning theory, this is going to be probably a repeat for you. But all I want to do is to recall that if I had a single distribution, I want to use samples from that distribution and learn a hypothesis that has near optimal error. And what I'm going to do is a very natural algorithm. It's called empirical risk minimization, or ERM. You've probably heard about it. And what it does is it just takes a number of samples, sufficiently large number of samples. And then what it does is that it takes the classifier or the hypothesis that looked the best on that sample case. So its loss or its error, it was the least possible on that set. So then what do I really need to say if I want the outcome of this ERM, which was computed on a sample set, to actually have some meaningful performance on the distribution? I have to say that I took large enough number of, like sufficiently large sample set, so that essentially every function's error, true error, the error is expected error on the distribution, was really well approximated on the sample set. In fact, if I just say that every function was well approximated to the degree like epsilon over 2, then whatever the ERM gives me can be at most epsilon worse than the optimal function. So this is really now about an estimation and whether or not I can estimate a lot of functions from the same set of data. So how do we do this? This is really when statistics comes in. Let's make it simple. Let's assume that I had a finite set of hypotheses or finite set of classifiers. So all I have to now use are two tools, concentration bounds and union bound. What does that mean? It just means that at the end of the day, I want to say that the probability that the empirical loss, this is evaluated on the sample set, versus the true loss evaluated on the distribution are far from each other is low. I want this bad event to be a very low probability bad event. And note that this bad event has to hold for all functions within a finite set of function classes. So if I took just a single one of these, then I just have this Haghtalab bound that tells me how quickly something from samples converges to its mean. So this is the Haghtalab bound for any fixed classifier. Now, because I want this to hold for every classifier, all I have to do is to take the union bound over the number of these classifiers. So this is really a simple way to think about this: union bound, Haghtalab bound, and I want this to be arbitrarily small, maybe a very tiny constant, and that tells me what the sample complexity would be. Now, the reason I'm doing this is that this is an offline way of thinking about problems. And so far, I feel like this week we've talked a lot about online way of thinking about problems, but this is even simpler than online. Now, what would have happened if the function class was not finite? Well, there's a concept called VC dimension. Good news is that we don't need to know what it means. All we need to know is that it essentially controls something that is very similar to the size of hypothesis classes. It essentially controls the effective size of the hypothesis. So instead of size of H, I just replace this with something that is exponential in VC dimension. Doesn't really matter. At the end of the day, what I get out of this is that, especially for the finite case, I want this to be very small. M, which is my number of samples, has to be like 1 over epsilon squared log of H. So that is the type of sample complexity bounds that we think about, okay? When you do have VC dimension bounds, this is what it looks like. Now, again, since we've seen regret more than error so far, they translate to each other really nicely. Like another way to think about this is that the average regret, which would have been that playing the role of epsilon, would have been square root of VC or log H divided by T. So that's just kind of translating to, if you've seen regret, this is essentially doing the same thing, but it's not even adversarial. Something just gave you samples from the same distribution. So this is for learning a single distribution. Are there any questions about this? It's just a mathematical exercise telling us how simple it is to learn from a single distribution. Okay, so let's come back. Now that we know how we can learn from a single distribution, what is sample complexity is, I want to do another thought exercise, which is that what can I actually hope for in terms of sample complexity of now k different tasks, okay? And in particular, k different tasks, the way we discuss them, not in isolation necessarily, the way we discuss them. And I want you to know, if you had to bet, what would you bet? So what is the range here? I have the sample complexity of a single distribution, single task, what we saw in the previous slide. I have k times the same sample complexity asymptotically, okay? I'm allergic to constants. So asymptotically speaking, k times the same amount, okay? Now, what do you think is going to require for solving this problem? Should I expect the sample complexity to be here, even more than k? Should I expect it to be between one distribution and k? And I mean, okay, we all know it's not going to be there. Okay, Shushi.
So I guess wouldn't the answer depend on whether you can draw samples from each of the distributions or just one? Or,
you have access to any distribution you want to draw from. So the D1 to DK, you can choose a distribution. Like you said, I want to sample from D3, and then you take as many samples as you want. Okay, think about like populations being like different cities. I go to a city and I decide that I'm going to Boston, and then I take IID from Boston. Or I decide to go to San Francisco. So that is important. You should be able to, you should have sample access to any DI. Okay. Now with that in mind, if you had to bet, who was this? Okay.
So you're fixing H and then you're sending K to infinity after fixing H? Or?
I think that's a good way to think about it, but I do want to like, let this be a conversation. So if I wasn't doing that, is there something that that you want to say?
I mean, it could be that H is very complex, but then I will let K be even large compared to the VC dimension of H, and then
right.
fix it, but maybe that's not realistic for many. That's
okay.
The nature of my concern.
Right. So that's true. If K is much bigger than BC dimension or much smaller than BC dimension, these fall in two different regimes. In particular, if K is much smaller than BC dimension, what can happen is that, let's say K is like 3, something like that. Then I can actually create 3 isolated learning problems that have nothing to do with each other. And at that point, I'm much closer to being here, right? But because we are thinking about asymptotics in K, let's allow yourself to play with K as it goes from 0 to infinity. So what happens there?
Log K sounds very possible.
Okay.
Like even in the online setting, you can sort of, you know.
So that's a very good question. That's a very good answer. There are 2 forces here that one should make you a little bit concerned, to make you feel like maybe this is going to take more than K distributions. And then there are some forces that tells you, actually, no, this is going to take less than K. And I feel like both of you have talked about why it could take less than K samples. And it's kind of like saying that, yeah, like learning problems can be related to each other. And sort of once they're related to each other, I shouldn't go above K. I should be here. And in particular, maybe log K. But forget about log or square root or whatever. Why don't you think, like, should you worry about it being greater than K? Or is there any force at least that concerns you to start with?
Just to one hundred percent, here's a sample complexity of learning. The worst case distribution, like the worst case sample complexity, K times. It's not, but you're saying that given D1 and DK, the sample complexity of learning D1 and sample complexity of learning D2.
Yes, that's a very good point. Let me clarify what I'm doing. When I say sample complexity of learning one distribution, I mean worst case distribution. I don't mean this to be as sum of the sample complexity of D1 to DK. In fact, you cannot get those results as easily. Yeah.
Are you allowed to violate, like, are you allowed to choose F from outside H? Yeah. Then it should be bounded by K.
Should be bounded by K. Okay. So let me just say that while you guys are very smart and you definitely know this, why a lot of people feel queasy when they see this, okay? It's because there are 2 forces, and one is the one that all of you identified, but I don't want to lose sight of the other one, because a lot of the communities that I mentioned actually work in this regime, and there are reasons for it. So what are these two forces? So the first force is the one that you identified, the fact that distributions could relate to each other. And in fact, if I keep the function class the same and I increase the number of distributions, I just cannot make too many independent problems. In some way, if I want my learning problems to be really far from each other, very different, I'm making this opt to be really bad too. And then because opt is really bad, it's not that hard to learn something that's trivially bad. Or they have to be very related to each other, in which case it really helps to sample from one and learn about the other. So that's the force that we all identify with, and that's really nice. The second one is the thing that does worry people, and I think it's good to think about it, which is that I need to give the same F. Okay, I told Daniel not to worry about it, but if you didn't know that you shouldn't worry about it, then you would have worried about it, and you would have thought that I need to coordinate. So even if individually, like I just told people to go learn a function for their own distribution and come together, there's no guarantee that I don't need any additional samples to actually learn a function that would agree. So this coordination should be something that is highly non-trivial and should it's usually a source of concern. And that's why a lot of communities work in this space, because they kind of worry about the fact that this kind of, they mostly are after the fact of saying that coordination is not a big problem. Okay.
So suppose the loss was the true now.
Mm-hmm.
If you want to find the mean of each distribution, what you're asking is, can I find a single number which is close to all the means?
Yeah, I think it's important, it's kind of nice to think about what F is representing here. Yeah.
So one-dimensional distribution that is which is closest to the. I agree with it. It's amazing that there's a single number which is close to all the means.
Exactly. And I think it's important here because you don't see that happening with the mean estimation, but it happens here. When I fix the function complexity class and I increase the number of distributions, I cannot have independent arms or independent distributions that much.
Just to respond to say, I don't think you're claiming that we get equally good by selecting one F, but we are satisfying the guarantee by selecting.
We are satisfying, that's true.
Difference.
That's true. Yeah. So okay. So I'm not trying to trick you. I just expected that at least half of you to worry about this, and that's why I put it on the slide. But you guys are so smart, so you didn't worry about it. But if you had to worry about it, what I would tell you to calm down is, this is about combining different functions, which looks very similar, like combining different experts. And we'll see why they're similar enough. And also to make you, again, really not to worry about this, I would say that, well, just think about the setting where there is no obvious misalignment between these. Do the thought exercise when I was in the realizable setting. Now, there is still coordination, but like it's kind of like saying that I have K different problems. One of them is the hardest. And I just need to really identify which one is the hardest. So you didn't worry about this, but if you had to worry about this, hopefully now you're very calm. Okay, so you're right in the sense that what we will show is something of the form log K. I will say that it's of the form log K because sometimes it's better than us and sometimes it's log K. And that kind of depends whether the function class is finite or not finite. It's really because there is something else that is characterizing this log K, which I don't want to go into for today.
I'm purely guessing, but is it like P? If it's the LP norm, is it P times, or is it?
No, it's actually a little bit, it's a different story a little bit. It is about how fast you can like use a dual space, but I don't think it's just P. I'll give you the tools and then you can just apply it to anything. Okay. Okay, since I did say this, to actually get this type of regime, we'll see that it's really important to use a distribution in a very specific way. And the communities that haven't used the distribution in those specific way, especially like the line of work that comes from federated learning and robustness, they fall in this category. And I will sort of tell you one reason they fall in this category in the next slide. So the reason here is that at a high level, to actually learn optimally, you need to coordinate across different distributions. You need to get them to interact, like especially if it was like a collaborative thing. You need to do this in a very adaptive way. What does lack of interactions look like? Well, it looks like in the setting, if I decided on the number of samples, learning rates, update frequencies, all of these in a non-interactive way. And what the problem with that type of approach is that it sort of ignores the fact that distributions have different difficulties. Because the only way that you can catch up with the fact that distributions have different difficulties is if you try to learn a little bit and then see like where you're not doing super well with respect to other distributions. So here really to benefit from this type of cross-learning, that the ones that we know that bring down the sample complexity from O of K, then what you need to do is to really allow these distributions to interact with each other. What is an example of this type of interaction? Is that the decisions we make about distribution I, whether about what predictor we are more likely to learn, or how much samples we are taking from it, what is update frequencies, all the things that you might think about in a learning algorithm, they have to depend on how well DI has done so far compared to the rest of the distributions. Okay, so it's not just about even its own behavior, it's about its own behavior compared with the rest of the agents. And that comparison is the important thing. To the degree that if you don't do this, if you're even adaptive but not in this way, kind of what you can get is that there's no way you can go below this O of K times learning a single class, okay? So this adaptivity is actually an important aspect of thinking about sample complexity. Recently, I've been calling it in my head as on-demand learning in terms of thinking about it as I decide where I need to do more and then I do more there. So that's kind of what I've been thinking about it. But sort of the takeaway here is that without an interactive protocol, these multi-distribution learning, especially if you want to think about it as collaboration, they're essentially as ineffective as not at all allowing the distributions to work together at all, okay? So this adaptivity and interaction is the key to getting better than solving K separate learning problems independently. Okay, so now that we know we need to do interactions, adaptivity, and coordination, how do we go about them? And luckily, we're in a week that we have learned so much about online learning and online processes because interaction, coordination, adaptivity, they're all things that get enabled by online algorithms. Just the way that we think about online algorithms has this kind of an adaptive thing that the next thing we do depends on how well previous options have worked out. So that has adaptivity back in it. But I don't want to just give you one other lecture about no-regret learning. What I want to do here is to go back to the unifying perspective that actually unifies no-regret learning and these problems, and talk more about that and how you would sort of fundamentally try to solve these problems optimally. And to do that, I want to go back to a min-max optimization perspective or min-max formulation of games. What is min-max? Min-max is one way to think about having two agents. One is trying to minimize some loss. The other is trying to maximize the other loss. And this is this shared loss that they have. And we know a lot of, we know a lot about how to compute these things. In particular, what this function f is an approximate min-max equilibrium. Why? It's because in the worst case, like it's a function we commit to, that in the worst case over the maximizing agent, we are only epsilon off from this opt. And this opt is something called value of the game. Okay, now again, this is actually something that throughout this week, we've come so close to directly addressing, but none of the talks so far directly address min-max games and no-regret learning. So I'm going to take a second detour to talk a little bit about them, just again, enough to understand the connection between them and no-regret learning, even though some of the talks we had came very close to explicitly stating them. So what is the relationship between min-max games, equilibria, and regret? Well, the min-max game, especially like, let's establish some formulation here. We have a game, it's 2 players. Whenever player 1 plays something, player 1 plays X and player 2 plays Y, then both of them get utilities, U1 and U2. Min-max game is one where the utility of one of them is minus the utility of the other one, okay? And in fact, we are going to just talk about losses as minus the utility of one of them, and the other guy is the minus of that loss. Now, from the game theory perspective, min-max, max-min, all these solution concepts are really nicely equivalent in these types of games. Essentially, we think about mixed strategies where each agent picks distribution over either rows or columns, and then what they get is the expected loss, here shown by capital L of P and Q. P and Q are distributions, capital L is the expected loss. And min-max versus max-min essentially says which player goes first and commits to a strategy. And the nice thing about these games, kind of like foundation of game theory in a sense, is that it doesn't matter. It doesn't matter who goes first because min-max and max-min are the same. Under some assumption, one way to think about it is that if X and Y are finite, which actually translate to what subset of what we're working on. So while the min-max theorem has been proved many decades ago, there was a really beautiful proof of it through no-regret learning only 3 decades ago. And that one I'm not going to give, but I'm going to tell you what it relies on. Essentially, it relies on thinking about online learnability as a way of dealing with min-max, because they're both about interactions with an adversary, okay? Like online adversarial, not stochastic, online adversarial learning and min-max. And one way to think about this is that I take my 2 players. One of them, I ask them to play a no-regret algorithm. The other one, it doesn't really matter as much. They could best respond if they want to the current thing that they see, or they can also use a no-regret algorithm if they wish. So what does this look like? Let's say that the maximizing player is the one that is playing best response. So it takes a distribution given by player 1, so that's PT, and it's trying to maximize it, and it just uses QT that maximizes this loss, okay? What does player 1 do? Player 1 is choosing PT in a way that compared to the best P at the end of time, it doesn't have regret. Both of these we know how to do. This is just take any online algorithm. This is best response, or do another online algorithm. And the nice thing about this is that the pair of the strategies that are the average of what people have played is an approximate min-max strategy, okay? That's all about the detour I wanted to take, just to spell out the relationship between regret and min-max. Because I now want to talk about one way of solving the problem I have through no-regret algorithms. It's not the approach I'll give you is not the optimal way to do it, but then I'll tell you the optimal way without going through too much details. Okay, so how do I do this? I want to think about, again, multi-distribution learning as game solving. I'm going to reimagine this problem as a game, and this was the game I wrote. And again, to repeat, all I care about is to find an approximate min-max equilibrium. And from the detour, what I learned is that what's sufficient to do to get an approximate min-max is to average that P's and the Q's that each player played, when one of them was a no-regret person, and the other one was a best responding. The thing is that here I'm switching the roles slightly. The minimizing player is this guy, it's the H star. And I'm asking him to actually best respond. And the maximizing player is this guy who's choosing the worst distribution. And I'm going to ask him to give me a no-regret algorithm, or to use a no-regret algorithm. Now, I'm going to have a no-regret algorithm, and if I can have a no-regret versus best response, let's just forget about this game. Doesn't matter what it is. If I can get no-regret plus best response, I can use the detour and I'm done. Here, there is an issue, which is that while I have a game, that game is not really defined. And well, that game is not known to me in the sense that the game loss function itself is unknown. So if I want to actually get either of these to work, the no regret versus and best response, what I have to do is essentially to do it with while I do not know the game. But it's okay. I don't know the game, but I can estimate it, hopefully, whenever I want, again from samples. So this is where sample complexity and how good your no regret and your best response algorithms have to be come together. Sort of the worse your regret, the longer you have to play this game. And presumably at every time you're playing this game, you need to estimate a loss function, which needs more and more samples. Okay. Of course, the better your regret algorithm or the better your best response, it's possible that it needs to be really accurate. So it needs very accurate information here, which means that maybe in the first place, it needed just too many samples. But this is the connection between the two. So here is the promised good but not optimal approach. This is the one that you're using a no regret algorithm versus a best response agent. Let's spell it out what we mean. So I said that the minimizing player is going to be the best responding agent. What that means is that let's look over what the maximizing player did. The maximizing player chooses one of the distributions from a mixture of them. So essentially the maximizing player has given me alpha 1 to alpha k. This is just a convex combination. That's his strategy. In a way, what the minimizing player wants to do is to really just find a function that minimizes error for this PT. It doesn't know how to do it without doing ERM. So it's just going to take a number of samples on this point to run ERM. Now, what is the maximizing player is going to do? This is our no regret type agent. So what he has to do is to maintain a distribution over the k distributions. These are weights. These are the alpha I that I talked about. And if you recall from earlier in the week, how did we actually maintain these weights? Something like multiplicative weight, hedge, even gradient descent. All what they were doing was that they would sort of evaluate how well you were doing on a specific arm. Each distribution is now an arm. And then they would increase or decrease the weight or the focus based on how well you've done. So what this max player has to do in order to come up with these weights is to, of course, have a proxy of how poorly that distribution has been treated so far, which again, we need to do it from some samples. So this is exactly where the samples are coming in. And this is also exactly where the interactivity is coming in, because the next time around I take samples depends on how well that distribution was doing, because that's defined by my alphas. In fact, another way to think about it is that the no regret algorithm is literally telling me how to procure the resources that I wanted, because alpha I fraction of the resources I'm taking per round is coming from distribution DI. That's kind of the meaning of having this convex combination and trying to learn something for that convex combination. Okay. So is the algorithm clear? What I'm going to do is to tell you why this algorithm works. And I'm going to do it by actually making it a little bit simpler on myself. I'm going to make this assumption, which is that the min-max, the opt is 0, just because it makes things easier. And it doesn't really actually, technically is not introducing too much of a challenge for what I'm doing. Okay, so let's do this. Okay, so let me write something that I did not write. So min player is the best response player, takes the PT, that was sum of alpha IT DI. And then what I want from this player is to say that whatever it learned, like let's say it was H of D, on P defined at time t is at most some epsilon prime. And this is going to be like, I don't know, epsilon over 10. Okay, that's the best response. What I want my maximizing player to do is it's going to decide these alpha ITs. I'm not going to write the no regret algorithm. It is a no regret algorithm if I knew exactly how to evaluate losses. Use hedge, use whatever you want. But let's say that it has to be based on this L of DI of previous like hypotheses, like let's say the last step. And since I don't know this, what I want to say is that the max player took enough samples so the estimate that it's using versus the true value would have also been like at most an epsilon prime. Okay, so these are the places where the samples are coming in. I'm not going to go into the detail of why it's okay to be a little bit off within your weights. It really doesn't matter. So let's assume that this epsilon prime for this case was at least 0. Like this guy was really no regret. In reality, it's just no regret plus another epsilon prime, which doesn't matter. Okay, now what I'm going to use is that since I use hedge or whatever you want, the regret of it, especially thinking about average regret, is something like log of k times t over t. Why log k? Because this is the number of actions for the second player, for the maximizing guy, because he's choosing one of the distributions. So that's where this is log k. Okay, now how is this all coming together? Well, what happens here, this is very similar to min-max theorem, even though I didn't prove it for you, is that let's see what the maximizing guy guarantees. So because he was a no regret person, then it's with respect to the max of IK, this is the benchmark, okay? I'm writing the average utility that it was going to have. Can I?
I think it's
Okay.
fair enough.
Okay. Good. Okay. So, okay. So what is this person, what is the type of guarantees that this guy can give? Remember, HTs are defined by the first player, but the second player is no regret with respect to it. So that would have been its benchmark. This is its like regret over T. And the actual utility that it got, or the actual loss that it gave, it was trying to maximize it, is going to be the average loss so far, which is the loss of HT on PT. PT was the mixture that I defined based on alphas, okay? Now, what did my best responding person guarantee to me? That at every time, this is at most epsilon prime. So this is at most epsilon prime, okay? And actually the regret, also the way I defined it, you know, if I think about, let's say that, another way to think about this is that run this algorithm for t equal 1 over epsilon squared log k. Epsilon prime squared, doesn't matter. Then this regret has already shrunk to epsilon prime as well. Okay, so what is this giving me now? It gives me the fact that if I think about a randomized learning, you know, a randomized classifier. Let's say that I call this a randomized classifier. What it really is that it draws a classifier from uniform distribution over the things I have learned. Okay, so these are the things that the player number 1 has learned. Then what is the expected error? Because this is random, expected over the randomization of this classifier. It's just really, this is going to be loss of any, evaluated on any DI. This HT is literally going to be the average over the distributions of, sorry, average over the classifiers of HT. Okay. Now, at the end of the day, I'm taking a max I. And this is what I have here, which is essentially 2 epsilon prime. Okay. That's the type of guarantee that I wanted to get. And the fact that I could be no regret and best responding from samples gave me that guarantee. Okay, now what's the sample complexity? I didn't tell you anything about sample complexity. When it comes to samples, now where am I using my samples? Here. And here. And I'm using them T many times. So it's something like every time step, I'm using 1 learning task worth of problems, which by the way was something like BC, well, let me just log. And also I'm using something like enough to estimate a single function, which is another like 1 over epsilon squared. So this is a good enough approach to give me something like 1 over epsilon to the 4 log k log f. It's not what I promised to you because the epsilon dependence is definitely much worse than it should be. But it's nevertheless an approach that can get the log k for you. Okay. So this is just a simple approach, not optimal, but a high level idea about how you would solve this type of problem. Okay. Now, with this in mind, any questions about it? With this in mind, how would you actually think about the optimal way of doing this? Well, there were several things that were wasteful. The no regret was wasteful. Too many samples, too accurate estimates. All of it was kind of wasteful. And the sort of unifying way to, again, think about this is that I'm trying to solve a game, that's stochastic game. And there are tools for this. So in fact, sort of the tools that are known for this are like one of them is stochastic mirror-prox algorithm. Not going to tell you what it is, but you can look it up. It's very good at solving games. And the main idea is that it is not a no regret versus best response. It's 2 no regret algorithms that are sort of intertwined with each other and they sort of work well with each other. And it's known to get really good bounds generally for games. Now, what is not sufficient, what doesn't necessarily come with stochastic prox is that stochastic mirror prox just assumes that it has access to this kind of like noisy estimates of something. That noise is not something that stochastic mirror prox itself controls. It just comes from a stochastic gradient. But what we can here do is we can actually control how accurate of an estimate we want at any given time for any given function. So if you combine these ideas, which the second type is closer to something like adaptive sampling methods, or just kind of more carefully choosing when you want information, when you really cannot get away without accurate information. If you put these together, you can design optimal algorithms. And once you do that, you get this type of a guarantee, the log k. Okay. This comes from 2 different works. The one that is for this kind of the agnostic, like the one I told you there, the smart way of doing that for realizability was actually an older work, but it's really nice thinking about mirror prox and doing this optimally for in the agnostic way is a work that's much more recent. And Eric Zhao is a co-author, is a student of mine who's worked on this. You should definitely talk with him, ask all the hard questions from him. So this is kind of like the approach that you can use to optimally solve these. Okay, I'm going much slower than I thought. Okay, so the takeaway, there are a couple of takeaways I want you to have from this conversation. One is that this was a unifying perspective. If you, again, see this type of a min-max, which you inevitably are going to see just thinking about generalizing from the recent history, at least, then it's good to think about the tools that are in your toolset and you can use them. But also that thinking about online learning, so far it's been mostly used in terms of thinking about, adversarial behavior. Here, we're really using adversarial behavior to actually design a nice medium for collaboration and interaction beyond adversarialness. So I think this is something good to think about as when you can control both ends, how it helps you with environment design. Okay. So the last bit, which I poorly timed myself, is going to be about a slightly different type of consideration. And especially thinking about the fact that my NORGAD algorithm was essentially telling me how to procure my resources, who to sample from. Sometimes these samples are quite expensive. If I go to a population and ask for more samples, it's not clear if they want to give me that. Some of the expensive, samples come from physical domains. Testing lead pipes, you have to actually dig someone's backyard to test their pipes. Nobody wants to be the house that has to do it unless they really have to do it. Medical settings, it's quite expensive to do that testing. So in all of these kind of more physical related domains, sampling is very expensive. And people are happy to do it if they can see an obvious benefit to themselves. But if it's not obvious that that benefit is to themselves and not to somebody else, maybe they don't want to do it. So if you're really going to be thinking about collaboration or multi-distribution learning, what we need to also understand is that how does it benefit all users, not just in terms of the accuracy, but also in terms of accuracy and information sort of trade-off. So the third question was that, how should we procure resources? And in a way, this is a call to action for going towards a theory for multi-agent sample complexity that has incentives baked into it. So what are some reasonable share of data? Let me tell you what are unreasonable share of data, because I think that's much easier to think about. So we don't want to have this unreasonable burden. One example of an unreasonable burden is that if I ask a distribution to give me more data than would have been absolutely necessary for that distribution to learn by himself, okay? That is not okay if I do that. Because essentially what I'm doing is that part of A's contribution is exclusively used to meet other people's accuracy, and it's not at all helping that person. This was something we defined. Both of them are something we defined. The first one is called individual rationality. In more detail, what this is really saying is that an allocation or procurement of resources is okay if, first of all, every agent's accuracy constraint is going to be met by it, okay? Which is up to now, we've taken this at the face value. And on top of that, if their accuracy could have been met by something that is smaller than what they would have needed to learn by themselves. Okay. So if that is met, this is an individually rational sort of learning or at least procurement mechanism. You are never asked to provide more samples that you would have needed to do to just learn your own distribution. That's the first point. The second point, which is that you don't want your data to be exclusively used for somebody else, is very similar in the sense that you still want the agent accuracy constraint to be met. But what you don't want is that you don't want an agent to be able to reduce the number of samples by a little bit and keep their accuracy being met, but then hurt somebody else. Okay, so that would be, again, a bad allocation, because I'm asked to provide something where part of whatever I'm providing is exclusively used for somebody else's benefit. How do I formalize that? Again, it should not be the case that I could have met my learning guarantee with something less if everybody else kept their current the amount of resources that they're providing. And this is something we'll call stable equilibria. Given the fact that I don't have time, I'm going to skip more formal treatment of them. But is there questions about what they were essentially trying to say? So they refer to two natural concepts. Individual rationality is an economics concept that essentially says that by joining a mechanism, you're never doing worse than not joining it. And not joining it is essentially like you do something by yourself. And stable equilibria is an analogous form of something like Nash equilibria, which essentially says that nobody has any incentive to sort of deviate unilaterally from the current scenario. Okay, so I'll skip the formal treatment, but I do want to say that why they matter They're obviously about welfare of the agents because we're talking about what is reasonable and what's not reasonable, but they're also about usability and stability of the systems over time. Especially like if you think about if people come to a mechanism, at first they don't know if the mechanism is stable or not, or if it's individually rational or not. And if they figure out it's not, then they'll drop out or they'll reduce how much they're providing. And then that makes the whole mechanism to work much worse for everybody else as well. And again, just continuing on the line of showing how current algorithms, current data sets do really poorly with this, surprisingly poorly with this, is that take a standard learning algorithm that's currently being used on federated over for federated learning. What you can see is that something like 60% of the agents can unilaterally reduce their contributions to 5% of their current rate. So if they were giving 100 samples, now they can just give 5. But of course, if they feel like they can do this and they do deviate, then the learning mechanism can't learn anything useful. So it's not that the learning mechanism was wasteful intentionally. It's just that it was really poorly assigning these resources and was trying to procure them in a really unfair and unreasonable way. Okay. So now that we know they're important, do they first of all exist? And how good are they? So in terms of existence, it's not hard to think about an individually rational allocation because all you need to do is to make sure nobody's giving more than they should have in the first place. You can just kind of learn in a non-collaborative way, like individually learn across tasks, and you can do it. So definitely learning mechanisms exist that are individually rational. Unfortunately, I cannot say the same thing about stable equilibria, but in most cases, they do exist. Now, what is a bad case for an equilibrium not existing? If every agent was so much better at solving not just their own task, but the next guy, then we could get into these bad cyclic behavior. So one example of this is to think about each of these agents. They can solve both their own task well and the next guy. Like whenever they solve their own task, whenever they take a single sample, they've solved the next guy's task too. So then what happens is that the first person starts sampling, solve their task, but they also solve this guy's task. So this guy doesn't need to sample at all. So they're not gonna sample. Nobody helped this guy, so this guy has to sample. While he samples, he solves this person's task. And now we go back and the first person doesn't want to have sampled. So this is not an equilibrium, and no equilibria sort of exist in this type of a bad cyclic behavior. This is very similar to why these cycling behaviors also happen in games when you're thinking about trying to get a pure Nash equilibria. And these games are actually like what you're trying to do is very similar to pure strategy equilibria. And they might not exist if you don't have continuous functions and continuous action spaces, because you can get this type of cycling behavior. Not going to go into too much more detail other than the fact that saying that if I had continuity, that's all I would have needed, and some kind of monotonicity, in the sense that the minimum thing you really need, and it's sufficient, is that if the loss was monotone decreasing in sampling effort, the more you work, the better it was for you. And it was Lipschitz, so it didn't drop too fast, or it didn't like get stuck for a while and then drop, okay? And since I don't have a lot of time, I'm not gonna give more intuition about this. Just saying that if you can randomize a little bit about how many samples you take, you can sort of address these problems. The last thing here is really about, okay, even if they did exist, are they okay? Are they so much worse possibly than my optimal collaboration? You know, I spent half of the tutorial really focusing in the middle about how to optimally learn. Would these incentives cancel all the efforts we did to a degree or not? Can we understand them? They don't cancel all the effort, but they do provide a significant challenge that we need to understand, which is that they might require collaborative resources much more than optimal collaboration would have required. And these bad equilibrium, there are these bad equilibria where some of the agents shouldn't at all sample if you want to be in an equilibria. And unfortunately, those are the agents whose samples would have been super useful. What's one example of this? At a high level, imagine you had a type of setting where this person's data set was very central, was very generic. And then there were whole different distributions, populations that only intersected with this generic thing in a little, like a tiny place. Okay. So the central agent, because their task is so generic, if they learned their own task really well, they essentially have given enough of an information for every agent here so that none of those agents need to sample. So in some way, the optimal way to do this type of sampling, if you didn't worry about incentives, is that the central agent should do all of the work because they're just really good at it. But because they're so good at it, it's the reason they're so good at it is because their task is so generic that if these guys' learning task was met, by default, this person's learning task would have also been met because it's just too generic of a task. So in a stable or rational setting, they should take no work. They should just rely on everybody else sampling. Now, when everybody else samples, because they're so different from each other, we need to sample a lot more. And ideas of this type can tell you that there is quite a big gap between optimal sample complexity and one that is either rational or, or stable. And that gap could be square root of k. This doesn't completely say that we completely ruined what we worked for the first half, because it's actually doesn't, this is about very specific type of distributions, the distributions where the opt is just way too small. We don't know if for reasonable opts, there is actually such a misalignment between incentives and optimality. And I think that's for those of you interested, I think it's really good to sort of go beyond the worst case here and try to understand incentives in a much more reasonable, less boutique way. Kind of the takeaway here that I want to have is that in some cases, the equilibria are quite structured in a good way, in a bad way. You saw one example where the structure of equilibria said that you have to be inefficient, but there are also settings that say that the utility and the loss of the agent, sort of some people have to do no work essentially. And with that, really this part, what I want you to take away is to think about new mathematical foundation that we need to propose. We don't yet have a good sense of it, but we do need to propose this. Okay. And I realized I even miscomputed the amount of time that I had. So I even kept you here longer than I thought I was keeping you here. So really just to recap, we asked some fundamental questions that I'm not going to repeat since I've kept you here for way too long. But if you're interested in this line of work, hopefully we can spend some time in the semester to think about how we should go about learning from multiple distributions. Thank you. Yeah. Sorry, I thought I saw